Which of the following general reaction types is characterized by there being a single reactant? It's obviously not combination. You gotta have two reactants to do that. Decomposition, possibly, yeah, because you got a complex going to simple, more than one simple. Combination would be something like, let's see. You have maybe an A and a B reactant producing a C. That's not always the case, but it's one good example. Decomposition would be the other way around. So B is the best answer for that one. Displacement, if you had, let's see, if you had AB plus C, and depending on what C is, let's say C is a metal, C would replace A. And exchange, lots of times these are aqueous solutions, not always, but very often. And then the A and the C would just swap. So you'd have CB plus AD. So that's A, B, C, and D. That's our only choices. So B only has one reactant, decomposition. So I'm gonna leave that down there so I can see it. Number 4. The proper assignment of oxidation numbers to the elements in the polyatomic ion SO3 2 minus. SO3 2 minus. Okay, so the oxygen is given, right? Unless it's a peroxide. If it's a peroxide, it'd be a -1 oxidation state. But if it's by itself, it's a -2 oxidation state. So if you have 3 of them, that means a total of -6, right? But this is a polyatomic ion, and you've got to have 2 minuses not neutralized. So I say hold 2 for the 2 minus, and that leaves -4, so sulfur has to be +4. So let's see, +4 and -2 is D. Okay. Right. Number 6. Which element is oxidized in the following redox reaction? All right, so we have, it looks like this one is balanced for us already. And 2 waters plus sulfur. Okay. So we know our rules. There's McCoy and Grimmett. I gotta just keep this thing up here with me. That way. Gonna be people missing labs. Lots of people missing labs. So, so you guys are going to have to look up your lab partners and be nice to them so they'll give you the data.
So we all could work together, but how many people?
Maybe. If you split up the labor, if you do, right, you can knock it out pretty quick if you do that. We'll talk about that because there might be a straggler or 2 come in.
Christy said she was coming for lunch.
I'm sorry?
Christy said she was coming for lunch.
Oh, really? Where is she?
iPhone.
Oh, iPhone.
She's iPhone too.
Okay. So the kids must be okay then. Or
I was up all night, so I didn't make it up in time to come to the class. So I'm gonna come to lab.
The lab, okay. You got somebody to watch the kids for you?
Yeah,
Okay, good. All right, oxidation. Which element is oxidized? Remember how we tell oxidation is loss and reduction is gain of electrons. So elements in their most stable state at room temperature and 1 atmosphere pressure. So this would be a zero oxidation state. Sulfur would be zero oxidation state. We know that oxygen would give it a -2. So this hydrogen has to be a +1, right, to balance out. And if this hydrogen, hydrogens are usually +1, unless they're combined with a metal, right? And then they're -1. But in this case, it's +1. So this would be a +1 for that one, which means a +2 total and -2 for that sulfur, right? So -2 going to 0 would have to have what? It would have to lose 2 electrons, wouldn't it? Okay. So we have a loss of 2 electrons per sulfur. And there's only 1 sulfur, so that's all there is. No, there are 2 sulfurs here, right? So that equation is not balanced. Notice that? 4 hydrogens, that's good. 2 oxygens, 2 oxygens. We need a 2 here. Okay. If we were going to balance the equation using redox as our starting point, then we would have to balance all the electrons. But in this case, we're just looking for oxidation reductions. Okay, so this loss of 2 electrons, this is the oxidized. So this H2S, the sulfur, is oxidized. Which element in the following is oxidized? The sulfur in H2S is oxidized. That means the oxygen has to be reduced. It goes from a 0 to a -2, so it gains 2 electrons per oxygen. All right. Number 7. That one's given out on me. Try this one. Which substance functions as a reducing agent in the following redox reaction? So we got methane plus, what kind of reaction is this? Well, it's oxidation reduction, of course, but it's also another type. Right? It's a combustion reaction. Remember, all combustion reactions are redox. But you have to have elemental oxygen in order to classify it as a combustion. Back to the question. Reducing agent. So the reducing agent is the species that is oxidized. So we need to find out which one's oxidized. That's 0, -2 plus 1, -2 plus 4, right? -4 for this one, +4 for that one. This one is +1, so it's +4. This makes it a -4. All right, so which one is oxidized? I think carbon probably, right? It goes from a -4 to a +4. It has to lose electrons. I'm curious how many electrons then to go from -4. The way I keep myself from making errors in this situation, I go to 0. How do I go to 0 from here? I lose 4 electrons. Then I go from 0 to 4, +4, I lose 4 more. So we actually have a loss of 8 electrons per carbon. C2. That one appears to be balanced. So there's your reducing agent, the one that's oxidized, the CH4. Right. Number 8. What is the change in oxidation number for cobalt in the redox reaction? Okay. So we have 2CO203 plus carbon and 4 cobalts and 3 CO2. I'm going to stop and make a point here. When you have C little o, that's cobalt. When you have C big O, that's carbon and oxygen. This is carbon dioxide in this case. So be careful with your capitalizations. I know some students have, from eons back, acquired the habit of block printing everything, capital block printing. And in chemistry, that'll get you in real trouble. Okay, so back to the question. Change in oxidation number for cobalt. So we got to determine what's the cobalt oxidation number here. If -2 for oxygen, -6 total, this is a neutral compound. So this one has to be +6 total or +3 for each one of the cobalts. And this cobalt is elemental. So it goes from +3 to 0. +3 to 0 is D. All right, let's see. What's that covering up? Collision. Okay. The minimum combined kinetic energy reactant particles must possess in order for their collisions to result in a reaction is called what? This is just definition. I mean, you got choices there. Which one looks the best? Not even a wild guess. You got a 25% chance of being right. Activation energy. That's the amount of energy that the two colliding particles must have in order for a reaction to occur. The minimum amount. Activation energy. Sometimes we write it like this. Sometimes we write it like that. All right, 13. Whether a reaction is exothermic or endothermic is determined by what? The best way to visualize this one is to look at the reaction diagram. Right, remember, this is progress of the reaction. And this is energy of all the species at any one time. So if we start off here with our reactants, then we need a certain amount of energy up here to give you, to make the reaction go. This is the activation energy. And then this is the energy of the products. Right, so this is activation energy right here. All right, what about the difference between here and here? Right? That's the enthalpy of the reaction. So, and that's what determines exothermic or endothermic. This has nothing to do with whether it's exothermic or endothermic, this part of it right here. This part of the equation is kinetics. This determines how fast the reaction goes. This is thermodynamics or equilibrium, right? And they can be treated separately, actually. So the difference in this energy and that energy, if if this is the energy, actually, no. What we've done is we've gone down in energy. So if you look at it this way, reactants yield products. Where does that delta H go? It goes over here. It can be considered a product, that heat. That heat was contained in here somewhere, in the bonds, and then it was released here. So that's exothermic. So to answer the question, whether a reaction is exothermic or endothermic is determined by how reactant and product potential energies compare. Which one's higher? This would be an exothermic situation. If we go backwards, right, it would be endothermic. You'd have to put a lot of energy into it and get not a lot back. So an exothermic reaction in reverse is endothermic, and vice versa. Okay, so that was, let's see. Pick up the pace here. Let's see, what am I missing? Reaction. Okay, 14. Which of the following changes is most likely to decrease reaction rate for the chemical reaction? Okay. We've got 2 carbon monoxides plus oxygen. Yields carbon dioxide. Yeah, 2 CO2s. Okay. Decrease the reaction rate. We want to decrease the rate of the reaction. Okay. Adding twice as much O2 to reaction mixture, that'll shift the equilibrium, but it won't change the rate of the reaction. Changing the concentrations, well, that's another topic actually. Adding twice as much O2 to the reaction mixture. Actually, the reaction rate, and like I said before, the rate and the reactants and products can be treated separately. So what we want to do in order to increase the reaction rate is to change this part of the reaction right here. You could consider this one without a catalyst. If you add a catalyst, it decreases the activation energy required, which increases the rate. So let's see. You don't want to add a catalyst because that'll increase the rate. We want to decrease the rate. All right. If we add any of these reactants, that means there's more probability of collisions, which would increase the rate. Okay. So what we want to do is either add more of the product or decrease one of these. All right. So adding twice as much oxygen would increase the rate. Tripling the temperature of the reaction would increase the rate. Right. Adding a catalyst would increase the rate. Removing some of the CO. If we can remove some of this, that will slow down the reaction. Uh, 15. Catalysts are correctly characterized by each of the following statements except one. The exception is, okay, catalysts, they can either be solid, liquid, or gas. Is that true? Yep, sure can. They lower the activation energy for a reaction. Yep, they do that. They do not actively participate in the reaction. Well, that's false. They are actively participating. What you see, though, on a microscopic level, they're intimately involved in the reaction mechanism. But what you see is the catalyst comes in one end on a macroscopic scale, comes in one end, comes out the other end, seemingly unchanged. But it does participate in the reaction. So C is the false statement. D is true. They are not consumed in a reaction. Right? However much you put in, comes out on the other side. All right. Which of the following is the correct equilibrium constant expression for this reaction? Okay. 4HCl, 17. 17. 4HCl in the gaseous state, so that'd be hydrogen chloride gas plus oxygen gas yields 2 waters as gas and 2 chlorines as gas. So this whole reaction occurs in the gaseous state. That means that we need to keep all these terms because their concentrations can change. Right? Remember that solids in a reaction, their concentrations don't change. So they're not included in equilibrium. Pure liquids are not included in the expression. So if this water were a liquid, we'd throw it out, right, for the expression. So the equilibrium expression for this one, KEQ, would be concentration of water squared times concentration of chlorine squared divided by concentration of hydrogen chloride to the 4th power and oxygen to the 1st power. So let's see which one fits that. C. They swap these two right here. But it's the same expression. Oh, here's the definition. Le Chatelier's principle. What is Le Chatelier's principle? A system at equilibrium, if disturbed, will respond in such a way as to mitigate that disturbance. So it looks like C maybe. If a chemical equilibrium is disturbed, the system will try and reestablish equilibrium. That's probably the closest one that you're going to get out of that.
I like how the body tries to maintain hemostasis.
Oh yeah. Le Chatelier is going on in your body like 9 miles an hour. And there are thousands of chemical reactions that are occurring at any one time, and each one has its own equilibrium state. Most of them are mediated by enzymes, right? And the enzyme is a special catalyst, right? It doesn't just, see, inorganic catalysts tend to work kind of, everybody's welcome, right? It goes forward and backwards, either way, it doesn't matter. But enzymes tend to be a one-way gate. Not all of them, but most of them do. So if you want a reaction to go this way fast, you need an enzyme. If you want it to come back the other way fast, you need a different enzyme. All right. That gives the body more control over the reactions, actually. Number 19. CO2 and H2 are allowed to react until an equilibrium is established as follows. What will be the effect on the equilibrium of removing CO from the equilibrium mixture? All right, so if you have CO2, let's see, gas, and gas, plus, I'm not going to write the gas in there because they're all gas, water, and CO. Okay, so if it's at equilibrium now, and we do what? remove CO. So we're going to take some of this and remove it. So if it's at equilibrium, which way is it going to shift? That way. So it'll consume carbon dioxide, consume hydrogen, and produce more water and carbon monoxide. So H2 concentration will decrease, H2O concentration will increase. D. That would be your best answer. All right, number 20. According to Le Chatelier's principle, which of the following changes will shift the position of the equilibrium to the left for the reaction? I'm going to save some time and not write it up there. What would happen if we double the concentration of N2? We want to shift the equilibrium to the left. So if we increase nitrogen, it's going to push the reaction to the right, correct? The way it's written. Decrease the concentration of ammonia. That'll push it to the right also. Increase the concentration of H2. That'll push it to the right. Right. What about triple the temperature? This is an exothermic reaction. So heat is a product term. If we increase the temperature, we're going to add heat to the product side. That drives the reaction backwards. Right. So triple the temperature is the correct answer for this one. And that was Haber's problem when he was coming up with this reaction. He wanted to take nitrogen and hydrogen and make ammonia so the Germans could make explosives. So the way he got around it was two things. He used a catalyst to make the reaction go faster. He knew he had to have the temperature up high, like 800 degrees Celsius, and high pressure also, in order for the reaction to even go. But in order to get a useful amount of product, he used a catalyst to make the reaction go faster, plus he recycled. He took the mixture and bled off some of it, cooled it down. The boiling point of ammonia is a lot higher, so it dropped out as a liquid, and nitrogen and hydrogen stayed in the gaseous state, and then he just fed it back into the reactor and just kept bleeding off the ammonia, and that drove the reaction to the right. All right, 22. In which of the following compounds does chlorine have an oxidation number of +5? Oh, okay. A, B, C, D, and E. E means none. Okay. A is HClO, hypochlorous acid, if it's in aqueous solution. KClO2 and CaClO3. 2? Yep. More than one correct. Or more than one. Okay. We're looking for oxidation state of +5 for chlorine. All right. Hydrogen is +1, oxygen is -2. So together, they make a -1. Right? -1 and +2, -1. So this one has to be a +1. Right. That's not the answer. This one's -2, so that's -4 total with a +1. So these two together make a -3. That means this chlorine has to be a +3. All right. We can approach this one two different ways. We can take the whole compound together. Let's do it that way. Or you can take this polyatomic ion separately. Either way works. So calcium is always +2. It's an alkaline earth. This one's -2 for a -6 here. And, but there are two of them, so that's -12. Right? -12, and let's see, -2, -6 times 2 is -12. and a plus 2, minus 12, and a plus 2 is minus 10. But we got 2 chlorines. So each chlorine has to be a plus 5 to balance that minus 10. Right, there's your answer. Yeah. Yeah, I think this one would be easier worked as a polyatomic ion. If you just take that, what is the charge on that ClO3? Has to be a -1. ClO3 -1. Now you can do -2 times 3 is -6, hold 1 out, it's -5, plus 5. I think that's easier. All right. I think this whole page is yellowed. In which of the following sequences sulfur-containing ions are the ions arranged in order of decreasing oxidation number for sulfur? All right, so which ones do we have? We have SO3 2 minus. Let's see, this is 23. SO3 2 minus. We have SO4 2 minus. We have S 2 minus. We have S203. S203 2 minus. That's thiosulfate. S2. Okay, that's everybody. We just need to determine this one's 2 minus charge. If this is -2 for oxygen, -6, hold out 2 for that, that's a +4. -2 times 4 is -8, hold 2 out, -6, this is +6. And -2 times that is -6, hold 2 out is -4, correct? That we have to balance, but we got 2 of them. So this would be a +4 total or a +2 for that sulfur. Now arrange them in order, decreasing oxidation number. All right, so the largest oxidation number is this one. So that's 1 and 2 and 3 and then 4. But there are only 3 in the list, so we have to find which one works. The highest one is sulfate. So sulfate, the only one that's got sulfate first is B. And you can check the others to be sure. Yeah, that fits. B is correct. All right.
B and C both has +5. So would that mean more than what?
They do?
Well, on here you said they answered B. You said it was C. And when you worked it out, they both had 5.
Is that true? Let's see. I gotta get a new marker. That one's crapping out on me. Okay. Calcium chlorate is true. C is +5. Let's look at B. KClO2, right? KClO2. KClO2. Okay, so this is a -2 for that oxygen, which is a -4 total. This one's a +1. So that's a -4 is -3. This one has to be a +3. Did my 3 look like a 5?
Well, you had +5.
Huh? Did I write +5 on the board?
Well, on the paper. It
On the
was.
paper.
Oh, the work problems.
Yeah.
Oh, that's an error.
And then you had a B.
Okay, I see where the problem is now.
That's where I was.
22. Why did I write +5 there? No, that's wrong. No. That should be a +3. Yeah, I know what I did. I counted -4 for the oxygens, and I counted the potassium as a minus. That made a -5 chlorine. Yeah, that was my mistake. Right, that's wrong. Right, it's only C is the only answer for that one. Apologize. Okay. Okay, 24. Which of the following reactions is non-redox? Non-redox. Well, let's see. What's the simplest way? I'm looking for rules, right? Nothing works. So we're gonna have to do these. Just calculate them. Calcium carbonate plus yields. Calcium oxide plus CO2. That's how they make concrete cement. They take calcium carbonate, grind it up, and run it through a hot oven. And the reaction decomposes this, drives off carbon dioxide, and makes lime. 2KClO3. Yep. This is another decomposition. 2KCl plus 3O2. This one's really easy to decompose. In fact, you can take a solution of that and dribble it on the floor and let it dry. And then when your instructor walks through or your lab assistant walks through and steps on it, it'll, wow. Because all it needs is a little pressure and it'll decompose. SO3 plus H2O yields H2SO4. Okay. All right, we're looking for the non-redox. So this is a -2. This is a -2, which is -4 total. This is +4. How about this one? This is +2. This is -6. So that's -4. This is also +4. And the calcium here is +2, -2. Okay, so this is non-redox. There's no change in the oxidation states there. This one's 0. This one's -2, right? So we can see right off the bat, this has to be a redox reaction. We don't have to waste any time doing the further calculations. We know that this elemental oxygen is 0 and that oxygen is -2. This one is -2 +1 -2 -6 here +6. This is +1 there, which is +2 here, -2, which is -8. So that's -6. This is +6. Right? That's a non-redox. So 2 of them are, more than 1. Okay. All right. 25. Which of the following statements concerning oxidation reduction is correct? Well, let me see. More than 1 or no correct are options. So we have to look at the A, B, and C to be sure we don't have more than 1 or no correct response. They cannot occur independently from each other. That's true. Yeah, that's true. When you have oxidation, you always have reduction. How about B? They accompany all chemical changes. We just showed that wasn't true. So B is false. They describe respectively the gain and loss of electrons. Oxidation, reduction. Oxidation is the loss, so that's reversed. It should be they respectively describe the loss and the gain. All right, so C is false. That means A is the only true one in there. 26. In the redox reaction, 4Fe plus 3O2, 12 HCl yields 6 water. Okay, it's got multiple possibilities. All right, we're gonna have to assess this one right down to its roots. Three oxygens. Oops. Left out a reactant. HCl. How many of them? 12. Well. Now the products. FeCl3 plus 6 water. See, is that balanced? Oxygens, yep. Hydrogens, yep. 12 chlorines, yep. 4, yep, that's balanced. Okay, so now we assess the redox, the oxidation states. -2 plus 1, -1. So that means this has to be +3. -1 plus 1. Okay. So iron is, let's see, are we talking about any numbers in here? This is yeah, we're going to put that in here. Okay, so this iron goes to that iron 3 plus, that means it's a loss. 3 electrons per iron. And that means there has to be a gain somewhere. Chlorines don't, hydrogens don't, oxygen does. So oxygen has a gain of 2 electrons per O. So we've got 4 irons here, which means 12 electrons total transferred. And here we have oxygens, 6 oxygens, yep, times 6 equals 12 electrons. So the totals balance out. Now, let's see, the question is, HCl is a reducing agent. Is HCl oxidized? No, nothing happens to HCl. Oxygen is the substance oxidized. No, oxygen's reduced. Right, it gains. Fe undergoes an oxidation number decrease of 3 units per atom. Decrease, it goes from a 0 to a +3. That's an increase of an oxidation number, right? So there are no correct answers there, right? So E has to be the answer. None of those statements are correct. Right. 27. There's the definition. In a redox reaction, the oxidizing agent is the substance reduced, or the one that contains an element that undergoes a decrease in oxidation number. So when they use that expression, it's a mathematical expression. If the oxidation number decreases, it goes more negative. And if the oxidation number increases, it goes more positive. It could still be negative, but it has to tend toward the positive direction. So C is the answer there. That one is correct. C. For a collision between molecules to result in a reaction, molecules must possess a certain minimum energy and. So we talked about the minimum energy already. That's the activation energy. That's not everything you need. In this collision, they have to be oriented correctly so that the reaction, so that the bonds that can be broken must be broken and then reformed in the process. So orientation is critical. They have a favorable orientation relative to each other when they collide. That C is the correct answer there. Those two factors must be observed in order for the collision theory of chemical reaction to be valid. All right, 31. How are we doing on time? Okay. Chemical equilibrium is reached in a system when you have an equilibrium, then the rate of the forward reaction and the rate of the reverse reaction are equal. So which one? Reactants are being consumed at the same rate that they are being produced. That's another way of saying it. C. Let's see, how about 34? We got the Haber again. According to Le Chatelier's principle, which of the following effects will occur if ammonia is removed from an equilibrium mixture governed by this equation? Kind of talked about that earlier. If you remove ammonia, you're going to shift the equilibrium to the right and make more ammonia. So the no, the concentration of nitrogen will not increase, it will decrease. Heat will be generated. Yes, right, because it's an exothermic reaction. If you remove NH3, then you're going to force the reaction to move further to the right and create heat, which is a product. So B is correct. Concentration of H2 will decrease. Yes, B and C are correct. So D is the answer, more than one correct response. All right, 35. For which of the following equilibrium systems will the equilibrium position shift to the left when a stress of increased pressure from a volume decrease is applied? All right, I guess better put each one of these up here. So we have two NO2s, two NO2 gas plus 7 hydrogen gas is in equilibrium with 2 ammonias plus 4 waters. Well, let's take them one at a time. Let's see. Shift to the left. So we want shift to the left when a stress of increased pressure. So we're increasing the pressure by decreasing the volume. All right. If we increase the pressure, the reaction is going to tend toward the side with the fewer moles, total moles of gas. So let's see. We got 9 on this side, and we got 6 on this side. So 9 versus 6 moles. So if we increase the pressure, the reaction is going to shift to the right. Right? And we're looking for the one that shifts to the left, right? So this one can't be it. How about the next one? CO gas plus H2O gas yields CO2 gas plus H2 gas. Okay, 1, 2, 1, 2, 2 versus 2. This one's not going to shift at all. There's no difference, right? You can increase the pressure all the way to infinity and nothing will happen. Well, no shift will happen, let me put it that way. How about C? H2 plus Cl2 is in equilibrium with HCl. Yeah. Okay, this is 2 and 2. Nothing's going to happen there either. Right, so there's no correct answer here. Let's see, curiosity just popped into my head. Okay. Look at this equation here. No. No. Yeah, there we go. 4 moles on the left and 2 on the right. If you increase the pressure on that one, it's going to shift to the right. So that's one of the reasons that Haber increased the pressure to dozens of atmospheres. Increased high pressure would tend to drive the reaction to the right, plus he removed product. Eventually he figured it out. And then Bosch came along and refined it. Okay, no, we're still in chapter 9. All right, 39. So in 39, we have to look at each one of these statements, 1, 2, and 3, and which of them are true. Right, so the first one, the only information needed to write the equilibrium constant expression is a balanced chemical equation, true, with physical state information for the reaction. That's not the only, yeah, that is. If the equation is balanced, you have your coefficients, which are going to be the powers of each term. And then you know which ones that you can use because you have the states. All right, so 1 is true. That's true. How about 2? Oxidation number of sulfur is the same in the species H2SO4 and SO4 2-. That's also true. We did an example like that before. You can determine sulfur by the entire formula or by the polyatomic ion. Either way, comes out the same. And 3, increasing the concentration of a reactant makes the collisions between the reactant and other reactants less likely because of more crowded conditions. Number 3 is what's known as stupid. Right, you increase the concentration of a reactant, you increase the number of collisions simply because there are more of them there. It's a probability game. So 1 and 2 are the only 2 correct ones, and that means B is the answer. Sometimes whoever writes these questions, they just kind of run out of possibilities and they just have to make something up. And as often as not, it's a stupid statement. Okay, 41, let's see, 45. Okay, here's another one. Got to look at the 3 possibilities and see which ones are true. Number 1, of the known atmospheric greenhouse gases, CO2 is both the most abundant and also the most efficient at preventing heat loss from the earth. That is patently false. Right. The CO2 is not the most efficient absorber of infrared radiation, which keeps the earth warm. There are several other molecules that are much, much more efficient. Methane's one of them. And it's not the most abundant. The most abundant gas, well, aside from nitrogen and oxygen and argon, the most abundant gas in the atmosphere is water. So 1 is false. How about 2? Ozone is a form of oxygen in which there are 3 atoms per molecule. That's true. That's ozone. Okay, so that one's true. A decrease in body temperature slows down the rate of chemical reactions. Yeah, that's true. In fact, the rule of thumb is for every change of 10 degrees C, the rate, let's say plus, you increase the temperature by 10 degrees, you get a rate doubling on average. We actually calculate in general chemistry, we calculate the activation energy that's required to give that rule of thumb. exactly. I think it's like 41 point something kilojoules per mole. Anyway, so we've got two of these are correct. B. (46). Assign the following reaction to one of the reaction classifications given in the response list. Okay, so what do we got here? It looks like we have two becoming one. That would be a combination reaction. Or a synthesis, excuse me, a synthesis reaction. That'd be my best bet. (49). Assign the following reaction to one of the reaction classifications given in the response list. Okay. Potassium cyanide plus hydrochloric acid yields hydrogen cyanide gas plus potassium chloride. That is one in which the hydrogen and the potassium exchange places. Notice if you put the potassium with the chlorine and the hydrogen with the cyanide, you get products. So that's a double displacement or a exchange reaction. I think when they say displacement, they're talking about single replacement or single displacement. Exchange reaction is where you have a double displacement. They swap partners. And that's a good way to execute condemned prisoners. Right? You have potassium cyanide in the bucket underneath their chair where they're strapped in. And you have this hydrochloric acid vial or something up here. Either you break it or you tip it. And when it drops into that vat, it produces hydrogen cyanide gas, which comes up, fills the room, and lights out. Otherwise known as a gas chamber. I don't know if it's humane or not. Nobody's ever come back from one to tell us. I suspect it's a lot less traumatic than electrocution. 52. You just kind of suffocate, right? Because what does cyanide do in the bloodstream? It displaces oxygen on the hemoglobin molecule. It attaches to iron irreversibly, or it's very strongly attached. You can remove it under extreme conditions. Put somebody in a hyperbaric chamber if they've been exposed to cyanide, they're still living. Put them in a hyperbaric chamber and pump the oxygen level way up, and you can eventually get that cyanide off of their hemoglobin. Otherwise, you actually suffocate at a molecular level. Right? Your hemoglobin is.
It's carbon monoxide.
Yeah. Yeah. It's a similar. Mm-hmm. Yeah. Cyanide is, let's see. Carbon monoxide is like that. I think like this. And cyanide is like this. So they have similarities there. In fact, I think cyanide is more strongly bound than carbon monoxide. Let's see. Where was I? Oh, oxidation number of sulfur on H2SO4. H2SO4. We can do this one whole. It's not a big deal. We can do it separate, or we can do it as the polyatomic ion, or we can do it the whole thing. So if this is +1, that's +2 total. This is -2, that's -8 total, which means -6. That's +6 for sulfur, which is D. 53. For the indicated element, select the correct oxidation number from the response list. Oxidation number of carbon in potassium bicarbonate. And we want the carbon. We're looking for that one. Okay, -2 is -6 total, +1, and +1 for potassium. So these together give you a -4. That's a +4 for that carbon, which is C. And what you'll find is in chemical reactions, most often, carbon can have an oxidation number from +4 to -4. It has a really broad, wide range. Maybe that's one of the reasons that it's the basis of this life form. When your cells start metabolizing carbon compounds, you don't want them to go directly from -4 to +4 to extract energy from them. That would be more like combustion, and you just burn up. So we take them step by step. 56. Consider the following redox equation. So we're told it's a redox, SO2 plus NO2 yields SO3, yep, SO3 plus NO. Choose an appropriate chemical formula from the list that identifies the oxidizing agent. So which one is reduced? That's the oxidizing agent. All right, so this is -2. That means this is +2. -2, -6, that's just +6. This is -2, which is -4 there, +4 there, and -2 here, -4, +4. So which one is reduced? Right. Sulfur goes from +4 to +6. It's oxidized. Nitrogen goes from, oxygen doesn't change at all. Nitrogen goes from +4 to +2, so it is reduced. So the NO2 is the species that provides the element that is reduced. D is the answer. Right. Are we ever going to get out of chapter 9? I hope so. We don't have all day. 62. All right, following general reaction equation, choose the correct form of equilibrium constant expression for this one. All right, so we've got the generics. This is a gas, and this is a solid, and this one is a gas. Right? So we're not going to use this one. We have to use these two. So the equilibrium expression, KEQ, would be Z squared over X squared. Or we could reduce that and say Z over X and square the whole thing. Mathematically, that's the same thing, just in case they do that to us. No, they didn't. So B is the correct answer, this one. But for calculation purposes, that works too. All right, 64. Consider the following equilibrium. Carbon dioxide plus hydrogen gas plus heat yields methane plus water. So this is an endothermic reaction. Heat is a reactant. Right? So determine the effect on the position of equilibrium when CO2 is removed. That's simple. If you remove CO2, that changes its concentration, right? Since it's a gas, you change its concentration, shifts the equilibrium to the left. Now, that's an important point to make here. When we say shift to the left, shift to the right, if you can't reference a balanced equation, that expression means nothing. Right? If we wrote that equation the other direction, it would be shift to the right. Right? So when you say shift to the left, shift to the right, you've got to reference a balanced equation in order to do that. Otherwise, you would say produces and name the compound or name the element. The reason I'm emphasizing that is because several of the questions in this exercise require you to say which way is shifted. So now, since we have a balanced equation to reference here, 66 and 67 are looking at, which one did I skipped over 65. Right, the same reaction for 66 and 67. So with 66, determine the effect on the position when a catalyst is added. What happens to the equilibrium when you add a catalyst? Nothing. It just happens faster, right? So it does not shift. How about 67? The effect on equilibrium when the volume of the container is increased. We decrease the pressure. So we've got how many moles on the left? We got 4 moles total on the left, right? And then on the right, we have 2 moles. Okay. So if we decrease the pressure by increasing the volume, the response of the system is going to be produce more moles of gas. So the shift would be to the left with that equation as written, which would be B. Okay. Still checking my work problems to be sure I'm kosher. That's good. Good to do that. Because these work problems things, they go through iterations, correct mistakes and so forth. Okay, I just moved into chapter 10, didn't I? All right. Okay, now scooch down to 3 and 4. What happened to my? Guess they're still there. They're just not on the front page. 3. In the reaction, N3 minus plus water yields HN3 plus OH minus. The Bronsted-Lowry base is. All right. So we're talking acids and bases here. Plus H2O yields HN3 plus OH minus. Bronsted, I assume that if it doesn't say which side is which, when it is looking for the Bronsted-Lowry base, it's talking about reactants. So we look at the reactants. Which one, a base accepts a proton, right? An acid donates a proton. So which one accepts the proton? When we look at the change from here to here, it looks like this one accepted a proton from water, right? So this would be the base. This would be the acid. This would be the conjugate acid. This would be the conjugate base. Okay. So A would be the answer, N3 minus. I think that's the azide ion. So 4. We're looking for conjugate acid-base pair, right? 2 conditions for for identifying a conjugate acid-base pair. So it'd be like an acid this side and a base that side. What you need is for the acid to lose only one proton, one hydrogen. And then the base that's in the pair has to be everything else left over. You can't add anything, you can't subtract anything else. It's just different by that one hydrogen. So let's see, NH4 to NH3, acid-base pair. Which of the following is not a conjugate acid-base pair? Okay, details. Right, so A is true. That is an acid-base pair. B, OH minus and O2 minus. Well, if this one loses a proton, right, it leaves its electron behind, which increases it by this amount. So that one is also true. That was kind of tricky when you look at it. H3PO4, H3PO4. If this one loses a proton, what does it have left? H2PO4 minus. Whenever you lose a proton, you leave an electron behind. So that means the charge becomes more negative by 1. So is that the one? Is that what it says? Yeah, that was true. How about D? CO2, CO3 minus. There are no hydrogens in that group, right? You can't gain, lose, can't do anything with hydrogens because there are none there, right? So that one's false. All right, how about this? Make some room here. In which of the following pairs of acids are both members of the pair strong acids? Right? What are our strong acids that we were given in our textbook and in our lecture? Right? Hydrochloric acid is one, right? Nitric acid is another. And by strong, what do we mean? The reaction, the ionization goes completely to product side. That's what we mean by strong. Okay. These two are strong. What's another one? H2SO4 is another one. Let's see, which of the following are both strong? H3PO4 is weak. Phosphoric acid, that's a weak acid. These are all strong. So A can't be it. Hydrogen iodide, I left that one out. All of the halogens, except for HF. HF is weak. Well, all of the halogen acids are strong. So that one would be strong. This one would be strong. This one would be strong. So those two, that's correct. B is correct. Both of those are strong. And then we look at the others. H2CO3, carbonic acid is weak. HC2H3O2 is vinegar. Right? Acetic acid is weak. Right, so the only one that has both of them strong is B. All right, 6. Which of the following pairs of acids are both members of the pair polyprotic? Polyprotic just means that there are 2 or more ionizable hydrogens. And so if it's got 2 or more hydrogens as the first element, right, if it has any other hydrogens in there, those are not acidic hydrogens. For instance, acetic acid, right? H2SO4 is polyprotic. HC2H3O2 is acetic acid. It's monoprotic. Right? Those other 3 hydrogens are bound and they're not released. So A is not the answer. HNO3 is monoprotic. C, there we go, acetic acid again, it's monoprotic. the last one, H3PO4 and H2C4H4O7 those are both polyprotic. C4H4O7. I wonder what that one is. Nothing comes to mind. But D is the answer. And you can tell because the first hydrogens in the formula are the acidic hydrogens. And we have 3 for phosphoric and 2 for the other one, whatever its name is. 7. Which of the following is produced in the first step of the dissociation of acid, H3PO4? All right, H3PO4. Now, we're using an abbreviated form here. We know that this hydrogen has to be transferred to a water molecule if you put it in solution. But for simplicity's sake, we're going to say it produces a hydrogen here plus H2PO4 minus. So H2PO4 minus is B. That's the first dissociation. Second dissociation, you just take this one, drop another hydrogen. You have HPO4 2 minus. Drop another hydrogen from that, you have PO4 3 minus. So phosphoric acid dissociates in 3 steps. A solution with a pH of 13.3. What number is that? 11. 11. If the solution has a pH of 13.3, what's the question? Oh, strongly acidic, weakly basic, strongly basic. All right. So on our scale of pHs, right, 7 is neutral. We go up to in the neighborhood of, we can go from 13 to 14, say, and down here we can go actually down to 0. So this is acidic. This is basic. That's very close to 14. I mean, it's just a hair under 14. That's strongly basic. That D is the answer to that one. Well, which of the following does not describe an acidic solution? Okay. A, B, C, D. That's it. Okay, for A, the pH is less than 7. pH less than 7, that's acidic. Right? So which one does not describe an acidic solution? All right, so that's an acidic, we can skip that one. The OH concentration is greater than 1 times 10 to the minus 7. It's greater than 10 to the minus 7. If the OH concentration is greater than 10 to the minus 7, which would make it like 10 to the minus 6, 10 to the minus 5, 10 to the minus 4, what happens to the hydrogen ion concentration? Right, it's less than 10 to the minus 7, which means it's basic. Right, that's basic, so that's false. Right, this one's true, this one's false because we're looking for an acidic solution, and that describes a basic solution. Right, so we have unique answers A, B, C, and D. We found the right one. We can stop there. 13. Yeah, 13. If the pH of a solution increases from 3.1 to 2.1, so pH goes from 3.1 to 5.1. The hydronium ion concentration does what? It's becoming more basic, isn't it? It's becoming more basic. So this concentration is going to decrease, but by how much? Remember, this is a logarithmic scale. You've changed the logarithm from 1 unit, 2 units. So that's 10 squared in logarithmic terms. So that's 100 times. So you decrease this concentration by 100 times, or 1/100th of its original concentration. Decrease by a factor of 100 is D. That's the point of this one. To see if you remember that that's a logarithmic scale. And this is a linear scale. Actual concentrations. 14. In which of the following pairs of salts will both members of the pair hydrolyze in water to give solutions that are basic? Okay. B, C, D. All right. Lithium chloride and sodium cyanide. Lithium chloride, sodium cyanide. If the cation is derived from a strong base and the anion is derived from a strong acid, then you get a neutral solution. Lithium hydroxide is a strong base. Hydrochloric acid is a strong acid. So this one will be neutral. I'm using a rule of thumb here. Sodium hydroxide is a strong base. Hydrogen cyanide in solution is a weak acid. So this one is going to be basic. So that doesn't answer the question. Ammonium chloride and ammonium nitrate. Okay. Let's see. We're looking for basic solution. Right down up here. We're looking for basic. Both of them basic. All right, this is a strong acid, and ammonium hydroxide is a weak base. So this would be acidic. This, the same thing here. Nitric acid, this would be acid. So that's not it. Sodium acetate. HC2H3O2 and sodium fluoride. So this one's basic. This one, sodium hydroxide is strong base. Hydrogen fluoride is a weak acid. So this one would be basic. Strong base, weak acid. This one's basic. So C should be the answer. Yeah, that's it. Both of them are basic. And we don't have any, like none of the above, two of the above, those types. So once we find our answer, we can stop. You remember that rule of thumb? Maybe. When you dissolve a salt in water, go back to the original acid and base that would have produced the salt and see what their nature is. Then you can deduce the pH of the, can deduce, not the pH, you can deduce the acidity or basicity of the solution. 16. If a solution is buffered at a pH of 9.5, right, then the addition of a small amount of acid will cause the solution to have a pH of approximately 9.5. Right? If it's buffered at that pH, it's going to stay pretty close to that. And they say a small amount of acid because you don't know where in the buffer range that 9.5 is located. Right? If it's close to the acidic side of its buffer range, then you add a little. If you had a lot of acid, you could exceed its capacity. And then the pH would drop precipitously once you're outside that buffer zone. So we said a small amount of acid. Number 20. Determining the concentration of an acid using acid-base titration always involves completely reacting a measured volume of acid with a known volume of base of a known concentration. If you're going to determine the concentration of the acid, look at it this way. If you have molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And this works for monoprotic acids and monohydroxy bases. Then you're looking for the concentration of the acid. This is your unknown. So you have a measured volume of acid, and then you titrate it with a volume of base of a known concentration. This gives you the number of moles. Then all you have to do is divide the volume of your acid into the number of moles here, and you have the concentration of the acid. So A is the correct answer. You need a base of known concentration in order to do the titration. Now, if you're titrating acids and bases that their stoichiometry is not 1-to-1, then you either have to use the stoichiometry of the equation to do the calculation, or use the calculation of normality. Right? We talked about normality, didn't we? Yeah. And if you're going to do acid-base titrations day in and day out, normality is probably a more efficient way to deal with it. '24. In which of the following pairs of acids are both members of the pair strong acids? We've been down this road before, haven't we? HNO3, HNO2 is weak, HNO3 is strong. H2SO4 is strong, H2SO3 is weak or weaker. HCl and HClO4, those are both strong. Hydrochloric acid and perchloric acid are both very strong acids. So C is the answer. In fact, if we look at the progression, remember when we were memorizing the, or not memorizing, but discussing the polyatomic ions, right? We had the chlorate type, right? Perchlorate, and then we had chlorite, and then hypochlorite, right? And we add a hydrogen to each one and put it in an aqueous solution, right? That gets rid of the charge. And now we have perchloric acid, chloric acid, chlorous acid, and hypochlorous acid. The strength of the acids increase as you add oxygens. So the strength goes like this. Right? This is a weak acid. This is not as weak, but still weak. This is kind of middle of the road. Actually, its K value is 1, but this is a very strong acid. So you strengthen the acid as you add oxygens to them. You don't have to remember that for the exam. I just thought I'd throw it in for free. 29. Which of the following indicates an acidic solution? All right. So A with a pH of 7.5 is basic. Just slightly basic. Hydronium ion concentration of 5 times 10 to the minus 4. 5 times 10 to the minus 4 molar is much higher than 10 to the minus 7 by 3 orders of magnitude. 2.5. So this is acidic. C, OH concentrations. Hydroxyl ion concentration is 2 times 10 to the minus 8 molar. Right? That, if it were neutral, this concentration would be 10 to the minus 7. But it's less than 10 to the minus 7, which means if this is less than neutral concentration, then the hydrogen ions have to be more than neutral, which makes it acidic. So more than one is correct. D is the correct answer. All right. So we'll skip a few. Oh, okay. So we have to look at 1, 2, and 3 and see if they're 37. 37. 1, 2, and 3. Okay. First statement. Both members of a Bronsted-Lowry conjugate acid-base pair must contain the element hydrogen. Not necessarily. Suppose the acid only has one hydrogen to lose. When it loses it, the base doesn't have a hydrogen anymore. Right? So 1 is false. The larger of the value of the acid ionization constant for an acid, the larger the value of the acid ionization constant, the weaker the acid is. That's false. The bigger the Ka increases, that's more acidic. It's a stronger acid than the lower value of Ka. All right, so how about 3? Weak acids cannot completely neutralize strong bases. Who says? Weak acids and strong bases can neutralize. Sure. Right. So that one's false. They're all false. Right? None of the statements are true. Now, when you do that, a weak acid and a strong base, the pH at which you have equivalence is not 7. Right? It's going to be above 7. It's going to be toward the basic side. 38. 1, 2, and 3. All right. Formation of a coordinate covalent bond is always part of a Bronsted-Lowry acid-base reaction. Formation of a coordinate covalent bond. You know, that could be true. Acid-base reaction. Right, there's your acid. There's your base. When this separates from that one, it leaves its electron behind. And when this separates from that one, its electron is here. So when the bond forms between OH minus and that one, the bond is produced by electrons from this species. Yeah, that's true. That's a coordinate covalent bond. Yep. Okay. So 2, the compound H2CO3 is both a strong acid and a diprotic acid. It is a diprotic acid, but it's not strong. Right? That's carbonic acid. That's what you get in pop. Right? When they put CO2 under pressure goes into the drink, and that's why the cap is sealed and the bottle is rigid when you buy it and you open it up. Especially if it's warm when you open it, it goes. Because the CO2 is coming out of solution, but this solution itself, H2CO3 is weak. You don't want it to be strong. I mean, it'll eat your tongue off, right? When you take a sip of it. Phosphoric acid's in there too. In fact, that's why you can take Coca-Cola and drop a nail in it and come back a week later and it's gone. It's not just the acidity, it's the phosphate, right? It forms iron phosphate in solution. Anyway, that was false. How about 3? The pH of a solution with OH minus concentration of 1 times 10 to the minus 8, 10 to the minus 8 is where they're saying the pH is 6.0. So what would the pOH be for this one? We did talk about that, doing the pOH, right? The log of this would be minus 8. The negative log of that would be 8, right? So pOH plus pH equals 14. That means pH equals 14 minus 8, which is 6. That one's true. So 1 and 3 are true. You have 2 true answers. B is the answer to that one. Ooh, got a bunch of these. Let me take a quick peek at these then. Because I think this type of question where they have to look at those 3. Yeah. I'll put those in the bonus section. So don't everybody applaud at once. 40. Because they do take some time. 1, in aqueous solution, Arrhenius acids undergo ionization and Arrhenius bases undergo dissociation. That's true. Because the acids, the hydrogen attached to the acid is covalently bound, so it must be ionized. You have to break the bond and make the ion. Whereas in the base, the Arrhenius base, you have the hydroxyl is already minus, HO minus, attached to some metal. And that's an ionic bond. So they simply dissociate. So 1 is true. Production of the salt NaNO3 through neutralization reaction involves the reaction of a weak acid and a strong base. This would come from a strong base. This would come from a strong acid, right? So their statement is false. They're both strong. 3. The ion product constant for water at 24 degrees C has the numerical value as 1 times 10 to the minus 14. That is true. 10 to the minus 14. That's equal to KW. Right, so we have 2 true values there. That's B. 41. What are we doing? Just about out of time. One, the two members of Bronsted-Lowry conjugate acid-base pair will always differ from each other by 1 unit of charge. Will always differ by 1 unit of charge. Conjugate acid-base pair. Yeah, I can't think of an exception. Right? When you have this and that, they differ by 1 charge. Or if this is charged, then it will decrease by, its not charge will decrease by 1 because the hydrogen leaves an electron behind. Yeah, that's true. An equivalent of an ion is the molar amount of that ion needed to supply 1 mole of positive or negative charge. That's definition. That's simple. In acid-base titration, the indicator changes color when the reaction between it and added acid is complete. The indicator changes color. I guess that could be true. Fundamentally, when you're using a color change indicator for an acid-base reaction, you want the color change to occur close to the time, close to equivalence of the acid-base reaction under investigation. right? So ideally, the indicator would change color when the reaction, when the major reaction is also complete. Right. So that being said, I would be willing to call that one true also. I think I would have worded it differently though. All right, so all three of those I would consider true. Oh, another one. Okay, one. All rainfall, even in unpolluted areas, is acidic. Is that true? Yep. Carbon dioxide. When the rainwater picks up carbon dioxide from the atmosphere, it makes, let's see, H2CO3, carbonic acid. Right, so all rainwater is acidic. So if you need water that's neutral, then once you've distilled it and put it in the bottle, you need to seal it tight. Or if you're going to use it continuously, what we used to do is remove the cap, and we have this device we screw on here, and it had a carbon dioxide trap. We have sodium hydroxide pellets in here, and as it drew air in to replace the removed water, it would scrub the air of CO2, and it wouldn't contaminate your water. You don't always need to do that, but in those cases where you do, that's how you do it. Okay, so this one's true. How about two? Blood plasma, interstitial fluid, intracellular fluid, three general types of body fluids all contain electrolytes. Yeah. Everybody knows that. Blood plasma is slightly acidic because ions it contains undergo hydrolysis. No, blood plasma is slightly basic. Yeah. Ever so slightly basic. What is it? 7.35 to 7.45, is it? I think. Very narrow range, buffered. Greetings. So that a 3 is false. So we only have 1 and 2. B is the answer to that one. Have y'all talked about buffering in blood yet? Or does that come next semester? When you get into chemistry, right?
Yeah.
Yeah.
Next semester.
Yeah, they'll give you a heavy dose of that when you get to it. The buffering systems. Actually, the buffering system is enzymatically, what do you call it? Refereed. Okay, 49. Select from the response list the compound or ion that best fits the description, reacts with H3O to produce HPO4 2-. Okay. All right, so if this is a reactant, and it's going to produce HPO4-, then this side has to have phosphate in it somewhere, but it's got to pick up that hydrogen. So if it's going to pick up a hydrogen from this one, that's the hydrogen it picked up. That means this reactant must be PO4 2-, excuse me, 2-, 3-. Then if it picks up a hydrogen from this one, that leaves you with water. And that plus neutralizes one of these minuses, plus the hydrogen's there, 2-. So that's PO4 3- should be the reactant D. Okay, 54. Good. about out of time, aren't I? Select from the response list for the acid that best fits the description. An acid that has more non-acidic hydrogens than acidic hydrogens. Okay, so the acidic hydrogens are sitting out here, and then the non-acidic hydrogens are going to be in this part of the molecule. And you need more of them, more non-acidics. So you had more hydrogens here than you do there. So A can't be because it doesn't have any. B is a good one. Yeah. C2H3O2. 3 is greater than 1. C, you got equal numbers, and D is like A, you got none to deal with. So B is the best answer here. 55. Select from this list an acid that completely dissociates in solution to produce negative ions with a charge of 1. Completely dissociates. That means it has to be a strong acid. All right, so we're looking for a strong acid. A is a strong acid, completely dissociates, and the anion or the conjugate base it produces is -1 charge. So A fits. The next one, acetic acid, is a weak acid. C is, let me see, what is that? Propionic acid, I think. It's a weak acid. H2SO4 is a strong acid. Hold on a second. HCl dissociates, not so ionizes to produce that plus that. So there's your negative charge and there's your 1 hydrogen. And this one, H2SO4, goes through, its first step is strong, right? That one plus HSO4 minus. You know what? That one's got 2 right answers. This completely dissociates. Now, if you go from here, right, this is a weak acid. That's a strong acid. That's a bad question because A or D could be right for that one. Okay. So if that one shows up on the test, you could mark either one of them. And if I count you wrong, call me on it. All right, 56. Okay. A salt whose dissociation produces equal amounts of 2 ions. All right. A salt whose dissociation. So A, B, C, and D. So we got to have a salt. Is KOH a salt? Nope. KOH is a base. How about sodium nitrate? Yeah, that's a salt. And it produces equal amounts. A mole of this for every mole of that. Right? So that's a good one. H3PO4 is an acid. That doesn't work. And K3PO4 dissociates, but it produces 3 of these for every one of those. Right? So it doesn't produce equal amounts. So the answer has to be B. How'd that get in there? X. Don't ask me. Okay, 71. Let's look at that one. What's the pH of a buffer that is 0.25 molar in the weak acid? So molar in the weak acid. And and 0.260 molar in the conjugate base. 0.260 molar in the conjugate base. And the pKa is 5.53. pKa equals 5.53. This one is primed for Anderson-Hasselbalch. Remember the equation? It should be, I should have included it with the exam. Let me check to be sure. Let's see. Useful information. Ooh. No, I didn't. Right. So if you come to class, yeah, was there useful information along with the this one? Anderson-Hasselbalch. Okay. You can have that one at your fingertips if you want. pH equals pKa plus the log of the base, conjugate base, divided by the acid. All right. So it's a simple calculation. 5.53 plus the conjugate base is 0.260 log. And the acid is 0.250. Okay. So we just need a little calculator. 0.26 divided by 0.25. 1.04, we'll take the log of that. Is 1.7 times 10 to the minus 2 plus 5.53. And I get 5.55 pH. That would be C. Okay. Now, if these concentrations are equal, that term drops out, right? The log of 1 is 0. 10 to what power is 1? 0. So that drops out, and then the pH would be that. That's the ideal buffer pH for weak acid, is equal to its pKa. I think that's it, isn't it?